Hello everyone. So in this video we are just going to see about another one application of branch and bound technique. In the previous videos we studied about two applications for a branch and bound technique. One is assignment problem, another one is 0-1 knapsack problem. In this video I am just going to explain the concept of traveling salesman problem using branch and bound technique. So, before going to see about how it is solved using branch and bound technique, I want to tell about what is a traveling salesman problem. So, traveling salesman problem, so here we are just having some given set of cities. So, how many cities here is? We are just having 4 cities in this particular graph, and all the cities it is connected by means of some edges. These edges denote the distance between every pair of cities. What is the basic concept problem behind the traveling salesman problem is we have to find a best tour such that each and every city should be visited exactly once and it should return to the starting point. That is the main concept. Each and every city should be visited exactly once and it should be returned to the starting point. What is the main concept here is the distance traveled should be a minimum one. So that is the main concept here. So the distance traveling should be a minimum one. So minimum one means, so what we have to do here is we have to reduce the cost. So this problem automatically comes under the minimization problem. So consider here, I'm just having some tour here. I'm just starting from 0. Next I'm just going to 1. Next I'm just going to 2. Next I'm just going to 3. And next I'm just going to 0. This is one of the tour. What is the cost in this one is 0 to 1, that is equal to 10 plus, and next one 35. So I'm just giving here as 35, and next 1 to 2 I'm just writing 2 to 3, that is 30 plus 30, and next one plus 20. So what is the total cost here is that is equal to 45 plus 75 plus total cost, that is equal to 95. Okay, this is the one of the tour. Another one tour I am just going to consider here as 0 to 3. I am sorry, 0 to 1 I am just starting here, 0 to 1. Next I am just going to 3. Next I am just going to 2. And next I am just going to 0. So this is another one tour. So very main important thing is each and every city should be exceeded at least exactly one time only. So what is 0 to 1 is 10. I am just taking here plus 1 to 3 means that is 35. The distance that is equal to 35. And 3 to 2, the distance is nothing but that is equal to, sorry, 3 to 2, the distance that is equal to 30. Then 2 to 0, that is distance that is equal to 15. So I'm just taking this one as one of the concept here. So see here, this is 2 to 3, 1 to 3, that is equal to 25. Okay. So 10, 25 plus 30 plus 15. What is the value? That is nothing but it is equal to 80. So which one is better, 95 or 80? 80 is better. So this is the concept of the traveling salesman problem. So we have to find the tool which is yielding a minimum cost. So minimum cost, that is minimization, is the basic concept in the traveling salesman problem. So in order to implement this traveling salesman problem, I am just going to use the branch and bound solution here. For this traveling salesman problem, in the branch and bound solution, how to get a solution is we are just going to create a state space tree. So that is the one of the main concept in this branch and bound technique. Very important thing is, so this is a minimization problem. So the bounding function what we are just going to use here is a lower bound function. We are not going to use the upper bound. Upper bound is meant only for the maximization problem. In 0-1 knapsack problem we are just going to use the upper bound, but here since it is a minimization problem, what bounding function we have to use here is the lower bound function. So that is, if the bounding value is greater than the better solution, means we are just going to ignore that one. So if it is having a lesser value only, we are just going to take that one. Depending upon that, for each and every node, if a node is explode, that is giving a partial tour. For each and every partial tour, we are just going to find out the lower bound function. Which lower bound function that is having a minimum value, that particular node will be explored. Other nodes are get ignored. That is the one main thing what we are just going to use in the traveling salesman problem. So in the traveling salesman problem, cost component is a very important factor here. The main thing is cost of reaching a node from the root. So from the root, likewise I told, we are just starting with an initial node. Each and every node I am just giving here is that is given as a partial tour. So each and every node we are just generating that is given as a partial tour. So on each and every partial tour, so we are just going to estimate the cost. This cost is considered as a lower bound only because this one is a minimization problem. So that is the minimum possible cost for completing the tour from the current node. So that is the main concept what we are just going to follow in the traveling salesman problem. So I'm just going to take this as a particular graph. So in this graph, totally we are just having how many cities means 5 cities A, B, C, D and E. So I'm just going to start with the initial vertex. I'm just telling that vertex as an A vertex. I'm just going to start with this A vertex. But initial bounding function I want to take here. How to take the initial bounding function is, so if, for each and every vertex we have to find out the cost. So how many vertex here? So this one I want to calculate the value for this one for the A vertex, this one for the B vertex, this one for the C vertex, and this one for the D vertex, and this one for the E vertex. So totally I am just having 5 vertex. All the 5 vertex I am just giving here. So from each and every vertex, I am just going to find out the smallest distance uh, that is neighboring two cities. So what is the smallest distance to the neighboring two cities here is, from A, we are just having 4 edges, 8, 1, 4 as well as 3. But the smallest distance is 1 as well as 3. So I am just going to consider that one, 1 plus 3. For B, the smallest distance, so here we are having 3, 6, 7, 9, but the smallest distance is 3 as well as 6. And for C, the smallest distance is 1 as well as 2. And for D, the smallest distance is 3 as well as 4. And for E, the smallest distance is 2 plus 3. So I am just going to calculate this one, summation of all the values divided by 2, I am just getting 14. So 14 is now considered as the lower bound. So this is the way of calculating the lower bound in the initial one. For each and every vertex, I am just going to find out the distance from each city to its nearest neighbor. That is the smallest distance we have to consider. Okay. So this is the way how we are just going to find the lower bound. So next case, from the A, what are the vertices I am just having? That is the path I am just having here is, from A we can go to E, from A we can go to C, from A we can go to D, and from A we can go to 3. So what are the possible? A to B is possible, A to C is possible, A to D is possible, A to E is possible. So in this, the first thing, I am just going to consider this A to B. So this is very important. A to B I am just going to consider here. A to B means from A we have to choose the two smallest distance to these neighboring vertices, neighboring cities. So what are the two vertices? While selecting this one, we should select A to B. That is the main concept. What the main thing is, we should select which one that is the smallest. Here A to B is the city we are just going to, the H we are just going to consider. So we have to select A to B. So here A to B should be selected. So the nearest smallest one is 3 as well as 1. And next one from B, A to B, that is must. So 3, another one is 6. I am just selecting here. So this is for A and this one for B. For C, the smallest one is 1 as well as 2. For D, the smallest one is 3 as well as 4. And for E, the smallest one is 2 as well as 3. So if we are just taking a H from A to B, that should be selected. So here what we are just getting here is the lower bound, that is equal to 14. Next, what the main concept I am just going to use here, I want to select a particular city that is called as A to C. A to C, that should be selected here. So what is A to C? That is the line it is given here. So automatically what is A to C is, I am just going to find out 1 as well as 3, and in for B I am just having, so A to C that cannot be selected, so I am just able to select 3 as well as 6. So the value that I am just giving here is 3 as well as 6. Next one, 1 to 2 I am just selecting, that is for the C node. C node, the very important thing is A to C, that should be selected here. And now I am just going to select another one node, that is 2. And for D, I am just selecting 3 plus 4 because this is the two smallest one. 5 and 7 are greater. So I am not going to select this one. I am just selecting the smallest one only, 3 plus 4. And next, for E node, I am just going to select 2 as well as 3. So what is the lower bound here? That is again, it is equal to 14. Okay, so this is the one thing I am just going to concentrate here. And next one, A to D. I am just going to select an A to D. I am just going to show this one by another one color. And just this is the next one, A to D. What is the weight of this one? 5. So I want to select 5. That is very important. Okay, two neighboring nodes. A to D means which one we have to select? A to D should be selected. So another one, smallest one, I am just selecting here. What is the smallest one? 1 is the smallest. So I am just going to select that one. So next, in case B node, so B node, two smallest one, 3, 6, 7 and 9 are there. Which one are smallest? 3 as well as 6. So I am just going to select that one, 3 and 6. And next one, for C node, we have to select 1 as well as 2. These are the two smallest one. And for this one, for D node, we are having two smallest, 3 as well as 4. But we have to select the node that is A to D is must because there is a path. So it's a partial tour. So I want to select this A to D. So instead of this 4, I am just going to select 5 as well as 3. So this is given as 3 plus 5, and for the E node it is 2 plus 3. So what is the lower bound value now? That is equal to 16. And for A to E, I am just going to represent by another one color. So that is A to B. The path, that is, this one is the path. So the value that is equal to 8. So I am in a situation to select 8 only. 8 should be selected, and again with this one, 1 is also selected. So 8 plus 1 is selected. And next was B, 3 as well as 6 are selected. Next was D, because A to E is selected. D, we are just C, we are just choosing the two smallest, 1 as well as 2. D, I am just selecting 3 as well as 4. And for E, so the smallest one is 2 as well as 3 only. But what is the normal concept? The partial tour from A to E. So which node should be selected? 8 should be selected. So instead of 3, I am just going to select 8 as well as 2. So 2 plus 8, that is given here. The total value that is equal to 19. So this is the first stage, first level of state space tree. So in this one, so two nodes it is having the lower bound value. So one is 14 here, another one is 14 here. So this is 16. So this is not selected because lower bound is we have to select the minimum value only. We are not able to select the maximum one. So this is not selected, and again this is also not selected. So I am in a situation to select this one. So this case we can see later. So basically I'm just going to explore the path from A to B. So this is the next one. A to B is selected. So B is not before C. So that is after C. So we are just not going to consider this one. I am just going to continue from this one. A to B is selected. A to B is selected. So next one, A, B, C is one path. A, B, D is another one path. A, B, E is another one path. So this is the concept I am just giving here. A, B, C, A, B, D. Another one is A, B, E. What is the next concept is we have to find the lower bound for each and every one. So for A node, what are the two smallest? A to B is selected. So that is fixed one. So I am just going to select the next smallest one. So that is 1 plus 3. And so this is for the A1 and this is for the B and this is for C and this is for D and this is for E. Okay, so this one for B, I'm just going to find out the smallest. So smallest one is 3 as well as 6. A to B should be selected. That is the standard one. So I'm just going to select 3 as well as 6. Why 6 is selected? A, B, C is the path. So what path I'm just going to consider here? A, B, C. So I'm just going to select as 3 plus 6. And next from C node, the two minimum cost is 1 as well as 2. But what is the path here? Path is from B to C. So I am in a situation to select this one. So what is the path I am just giving here is 1 plus 6. And for the D node, so two smallest one, 3 and 4. And for E node, two smallest one, 2 plus 3. So what is the total cost is 16 is the total cost. So similarly, what is the next one is A, B as well as D. I am just going to concentrate on A, B, D. How to calculate this one? A, B, D. So I am just changing the color in this one. A, B, D. So this is the path. So I am just going to take the path as A to B, we are just taking one path and another one path from B to D. So this is the actual path we are just taking here. For A, it is 1 plus 3 because the A to B we have to select here. And for B, the very important thing is 3 we are just going to select because it is on the path. But we are not able to select this 6. What part we have to select is we have to select this 7. So I am just going to select 3 plus 7. And here for C node it is 1 as well as 2. And for D node it is 3. It is not 4. Instead of 4 what we have to select is we have to select 7. So I am just selecting 7 here. And for this E node I am just going to select 2 as well as 3. So what is the lower bound here? Again it is 16. And the last one is A, B as well as E. So one node that is normally selected here, that is normally called as D node. I am just going to select this one. So that is an important concept what we are just going to use here. This node is selected. So A, that is no problem, it is 1 plus 3. But B, we have to select this 3 as well as another one B to E we have to select here. So that is 3 plus 9. So C is 1 plus 2 and again here it is 4 as well as 3. And but here we are just having a change. We are not able to select 2 as well as 3 because the partial path from B to E. So I am just in a situation to select 2 as well as 9. So that is normally given as 2 plus 9, the value that is equal to 19. So which one is having the minimum value? So 16 as well as this 16. So we are just going to explore these two one day. We are not going to use this one because this is having a higher lower bound value. So next one, going to the next one. So we completed up to A, B, C. So that is the situation we are just having here. A, B, C up to this one we completed. What is the next from? To D, then to E as well as A. So to A, B, C, then we are just going to D, to E as well as A. So this is the concept. A to B, we are just giving B to C. This is one part. Again, from C, I am just going to D, then I am just going to E, then back to A. So this is one path I am just getting here. So what is the lower bound value here? So we have to take 3 as well as 1. So what are the neighbor paths? We are just going to take here. Similarly, we are just going to calculate what is the lower bound value for each and every one. The lower bound value for this one, that is equal to 24. This one is equal to 19. This one is equal to 24. And this one is equal to 16. Okay. So compared to this one, so which is having a very lower bound value is this path. So from A to B, I'm just going from A to B, then to D, then to E, then to C, and then to A. So what is the bounding function of this one? That is equal to 16 only. Comparing, so which one? First one we are just having 24 here, here we are just having 19, here we are just having again 24. So among this one is the better one. So that is normally called as an optimal tool. So this is normally we are just taking as an optimal. That is the best solution, optimal solution. I am just checking here. So compared to this one, the next best solution, that is nothing but A, B, C, E, D as well as A, which lower bound value, that is nothing but that is equal to 19. So this is the state space construction of particular traveling salesman problem using branch and bound algorithm. So I hope we understand this one. So we can see the other normally problem solving techniques in the subsequent video. Thank you.